The earliest understanding of planets was based on a simple, comforting belief that every world circled a parent star. Early 20th century observations revealed a universe that appeared highly organized, with each planet held firmly in place by the predictable pull of gravity. This assumption guided astronomical thinking for decades. The limited tools of that time, using only visible light, meant that many cold, faint objects of the cosmos remained completely hidden from view. As our instruments slowly improved, astronomers began to pick up subtle infrared signals that did not match any known type of object. Infrared light is a gentle radiation emitted even by cold bodies. Sensitive detectors eventually found small, dim sources moving slowly and deliberately against the distant star field. These objects were too bright for an asteroid, yet too faint to be a star. It was then that the quiet concept of a planet without a permanent home first started to emerge. Our understanding of these mysterious objects deepened as infrared sky surveys expanded their coverage. Projects like the 2-micron All-Sky Survey and the Wide Field Infrared Survey Explorer revealed the widespread existence of these isolated planetary mass bodies. This challenged the deeply held assumption that planets must form only within the swirling protoplanetary disks around stars. The discovery of rogue planets showed that the universe allows for a much wider range of outcomes. A likely explanation for their existence involves powerful gravitational interactions during the early stages of system formation. When several young bodies form close to one another, their combined gravity can disrupt orbits. A close encounter can impart enough energy to a young planet to eject it completely from the system's gravity. The exiled world then becomes a rogue planet, drifting alone through interstellar space. Another fascinating possibility suggests a direct formation through the collapse of gas clouds that are too small to ignite nuclear fusion, the powerful process that fuels stars. In this scenario, a cloud can quietly collapse into a planetary mass object without ever becoming hot enough to shine. This shows us that the line we draw between a planet and a star is far more complex than our early definitions suggested. As the data slowly accumulated, astronomers began to realize that rogue planets might, in fact, be numerous. Some estimates suggest that our own Milky Way galaxy could contain billions of these isolated worlds. Their extreme faintness and slow movement make them difficult to count precisely. However, techniques such as gravitational microlensing provided new insight. This method does not depend on the brightness of the lensing object, allowing even dark, cold planets to gently reveal their presence. The idea of rogue planets adds a new dimension to the structure of our galaxy. Instead of being confined to the ordered boundaries of planetary systems, many worlds drift independently, shaped only by the weak gravitational tides of the Milky Way itself. These planets travel through regions where starlight barely reaches them. Though the surface temperature of such a world would be unimaginably low, internal heat from radioactive decay and leftover formation energy could maintain warmer, deep layers far below the frigid surface. This internal heat could potentially support vast subsurface oceans under thick ice layers, much like Jupiter's moon Europa. These distant analogs show us that life may not always require direct sunlight, but rather only a stable source of energy and protective conditions. The quiet recognition of rogue planets has fundamentally reshaped modern astronomy. They demonstrate that planetary formation is not a simple process restricted to circular orbits around a star. Instead, it is dynamic and sometimes violent, revealing a universe filled with far more variety than earlier generations could have ever imagined. A planet forms inside a protoplanetary disk, a wide ring of gas and dust surrounding a young star. Small grains collide, grow, and settle into stable orbits. Gravity holds each world close to its star, creating the traditional picture of an orderly planetary system. A planet becomes detached from its star when the early system experiences significant gravitational disturbances. Large planets forming close together can disrupt one another's orbits. A close encounter may accelerate one planet to a speed above the system's escape velocity, the minimum speed required to break free from the star's pull. Once this occurs, the planet leaves the system entirely. Simulations in the late 20th century showed that these ejection events are common outcomes of chaotic interactions. Even small differences in the initial layout of young planets can lead to dramatic changes in their long-term behavior. The moment a planet is ejected, it transitions from a warm, illuminated orbit to the cold environment of interstellar space. Its atmosphere may freeze and collapse, and the world enters perpetual darkness. A simple comparison can be made to a ball on a rotating playground carousel. When the ball stays near the center, it moves predictably. If another object pushes it strongly enough, the ball flies off the edge. A planetary ejection follows the same mechanical principles, only scaled up to astronomical distances. Infrared surveys, such as the Wide Field Infrared Survey Explorer, WISE, strengthen the evidence for these free-floating planets. Infrared light reveals faint heat from objects that no longer receive energy from a star. These worlds retain internal warmth from radioactive decay and leftover formation energy, making them detectable against the cold background of space. Some planets retain their moons during ejection. If the moon orbits close enough, the gravitational bond remains intact. These small binary systems then drift together through the galaxy. Their long-term paths are shaped by the Milky Way's overall gravitational structure, influenced by stars, gas clouds, and dark matter. The existence of planets detached from their stars indicates that planetary systems are active and unstable environments. Collisions, migrations, and gravitational interactions continually reshape them. Rogue planets highlight how these natural processes can produce outcomes far different from the early idea of stable, orderly orbits. A planet loses its place in a solar system when the gravitational forces that once held it in balance become disrupted. During the early stages of formation, a young system is crowded with growing planets, fragments of rock, and swirling gas. Each body pulls on the others through gravity. These forces shift orbits, modify paths, and create instability over long periods. The stability of a planet depends on its distance from its star, its mass, and the presence of neighbors that may exert rival gravitational influences. Computational models developed in the late 20th century showed that planetary systems naturally pass through phases of disorder. As planets grow larger, their gravity becomes strong enough to reshape the environment around them. A young giant planet can move inward or outward depending on interactions with the gas in the protoplanetary disk, a process called planetary migration. When it happens rapidly, it can disturb smaller planets, pushing them into new orbits. A planet becomes vulnerable to ejection when its orbit stretches into a region where the gravitational pull of nearby planets overcomes the stabilizing pull of the star. A close encounter between two planets can transfer energy from one to the other. If the transfer is strong enough, the lighter or less stable planet is accelerated outward. Once its speed exceeds the system's escape velocity, it breaks free entirely. An everyday comparison can be seen in a crowded parking lot, where cars move in tight, constrained paths. If one car suddenly speeds up or changes direction sharply, it can push another car toward the exit lane. In a planetary system, gravity acts like the momentum transfer in that scenario, guiding one body toward a path that leads out of the system. Observations of exoplanet systems provided additional insight. Many systems contain large planets in unusual orbits, indicating that they likely experienced significant gravitational events in their past. Some stars show infrared excess or debris disks that may represent the remains of disrupted planetary bodies. These clues support the idea that ejections are a natural part of system evolution. Once a planet loses its connection to its star, its orbit becomes defined only by the gravity of the galaxy. It no longer has a stable source of heat or light. The surface cools quickly, and volatile materials may freeze solid. However, the planet's core can retain heat for millions or billions of years. This internal heat may sustain subsurface oceans beneath layers of ice. Rogue planets that formed through ejection differ from those that formed directly from collapsing gas clouds. The ejected ones often retain signatures of their earlier environment, such as layered interiors or chemical compositions enriched by the protoplanetary disk. These features help scientists trace their origin, even when the planet now drifts alone. Studying how a world becomes homeless clarifies the dynamic and complex processes that govern planetary evolution. It shows that the early stages of a solar system are shaped not by calm development, but by continual competition between bodies. The outcome can be a stable, long-lived system, or a scattered collection of planets, debris, and isolated worlds traveling through interstellar space. Early infrared surveys revealed that the space between stars contains far more objects than previously expected. Many of these objects emit only faint heat, making them nearly invisible in visible light. As astronomers expanded mapping programs, a growing number of isolated planetary mass bodies appeared in the data. These bodies lacked the surrounding brightness, radiation, or orbital signatures that normally identify planets orbiting a star. Their solitary nature suggested that a hidden population of rogue planets drifted through the dark regions of the galaxy. Infrared detection is effective because even cold planets emit small amounts of thermal radiation. Instruments such as the 2-micron All-Sky Survey and the Wide-Field Infrared Survey Explorer scanned large sections of the sky, recording these fainter emissions. The brightness levels were too low to match small stars or brown dwarfs, and their motion patterns did not align with nearby asteroids. Over time, the detections formed a consistent picture. Our galaxy contains many sunless worlds. Furthermore, gravitational microlensing provided additional confirmation. Microlensing occurs when a massive object passes in front of a distant star. bending and magnifying its light. This effect reveals the presence of the foreground object, regardless of its temperature or brightness. Several microlensing events indicated planetary mass lenses with no associated star. These measurements made it clear that rogue planets were not rare anomalies, but part of a widespread, unseen population. The distribution of these objects suggests that they inhabit regions where starlight barely reaches. Their surfaces may be hundreds of degrees below freezing, creating a dark environment where even reflective materials absorb more heat than they radiate. Without a nearby star, these planets travel quietly through the Milky Way's gravitational field, influenced only by large-scale forces such as spiral arm density waves and encounters with passing stars. To put this simply, imagine small boats drifting on a calm lake at night. Without a nearby lighthouse or visible shoreline, the boats appear lost in the darkness. Yet each one follows currents and subtle motions of the water. Rogue planets behave similarly, moving along the gravitational currents of the galaxy rather than following the predictable orbits found inside solar systems. Astronomers now consider several possible origins for this hidden population. Some rogue planets were likely ejected from forming systems through gravitational interactions. Others may have formed directly from collapsing gas clouds that never became dense enough to ignite as stars. A small fraction could be remnants of disrupted systems, where collisions or close stellar encounters scattered their worlds. The overall number of rogue planets remains uncertain. Estimates vary widely, from millions to billions within the Milky Way alone. Their faintness makes them difficult to detect individually, and most are likely too cold to produce detectable heat signatures. Continued microlensing surveys help refine the estimates by capturing rare alignment events that temporarily reveal their presence. The existence of a large, hidden population of rogue planets changes the way astronomers view galactic structure. Instead of a galaxy composed primarily of stars and their systems, the Milky Way contains countless dark, isolated worlds drifting between them. These planets challenge the traditional idea of planetary environments and highlight the vast diversity of conditions found throughout the universe. Early observations of the night sky relied primarily on visible light, a narrow portion of the electromagnetic spectrum. Most telescopes built before the mid-20th century could not detect objects that emitted only faint heat. Because of this limitation, astronomers assumed that all planets must orbit stars. Planets without sunlight would not reflect enough light to be seen, and their thermal emissions were far below the sensitivity of early instruments. The absence of evidence was interpreted as evidence of absence. Planetary detection methods in the early era focused on predictable stellar signatures. The transit method requires a planet to pass in front of a star, causing a measurable dip in brightness. The radial velocity method detects the subtle wobbling of a star due to the gravitational pull of orbiting planets. Both methods depended entirely on the presence of a star. Rogue planets, having no parent star, produced none of these signatures. As a result, the tools simply could not reveal their existence. Infrared astronomy began to advance with the development of detectors capable of measuring small amounts of heat radiation. Infrared light comes from objects that are cooler than stars, including planets, brown dwarfs, and dust clouds. The first infrared sky surveys revealed many faint sources that did not match known astronomical categories. These signals were too cold and too dim to be stars, yet they were more massive than simple dust clumps. Several challenges prevented astronomers from immediately identifying these objects as planets. Early infrared data contained large amounts of noise caused by atmospheric interference and limitations in detector design. Thermal emissions from Earth's surface and the telescope itself often overwhelmed the faint signals from distant objects. Removing this noise required improved cooling systems and careful calibration. Microlensing added another layer of complexity. While this method does not rely on brightness, it depends on the rare alignment of a foreground object with a background star. Early microlensing surveys lacked the coverage and precision needed to detect small lenses. Only after large-scale programs were developed did planetary mass microlensing events begin to appear consistently. Consider the analogy of trying to spot a small, unlit boat at night on a lake. If the observer uses only a flashlight, the boat remains invisible unless the beam shines directly on it. As soon as a thermal camera is used, the boat becomes visible through the faint heat it emits. Rogue planets required a similar shift in observational tools. The difficulty in noticing these planets also came from assumptions embedded in early astronomical models. Researchers expected planets to form and remain within stable, organized systems. Textbooks described solar systems as isolated and orderly, with well-defined orbits. These assumptions shaped the interpretation of observations. Data that did not fit the model was often attributed to errors or noise. As technology improved, detections accumulated. Infrared surveys, microlensing campaigns, and refined modeling gradually provided a clearer picture. The number of isolated planetary mass objects grew steadily, and the consistency of the findings removed earlier doubts. It became clear that the limitation was not in the universe, but in the tools used to observe it. The difficulty astronomers faced in noticing rogue planets illustrates how scientific understanding evolves. Improvements in technology reveal phenomena that were previously hidden, and long-standing assumptions must be updated to match new evidence. Rogue planets now represent an important component of galactic structure, showing that the space between stars contains more variety than early observations suggested. A rogue planet without a star experiences a dramatic drop in surface temperature, yet it does not cool uniformly. The interior of a planet holds heat generated during its formation. As material collapsed under gravity, gravitational energy converted into thermal energy. Much of this heat slowly escaped into space over millions of years, but a portion remained trapped deep beneath the surface. Radioactive decay provides an additional long-term heat source. Elements such as uranium, thorium, and potassium release energy as they decay into lighter elements. This process occurs steadily and independently of external light. Even a planet drifting through interstellar space continues to receive this internal heating, although at levels far lower than those produced by a star. The structure of a rogue planet determines how well it retains this internal heat. A thick rocky crust acts like insulation, slowing the flow of heat from the interior to the surface. Beneath the crust, the mantle may remain partially molten for long periods. Some planets also contain large amounts of water ice. Under thick layers of ice, internal heat can create a subsurface ocean. Moons such as Europa and Enceladus show how internal heating can maintain liquid water far from the Sun. The process is comparable to a thermos bottle. Even when the outside air is very cold, the insulated walls trap warmth inside the container. A rogue planet behaves similarly. Its exterior remains frozen and dark, while deeper layers retain heat due to the planet's structure and gradual energy release. Infrared surveys detect this internal warmth as faint thermal radiation. Although the surface temperature may be only a few tens of degrees above absolute zero, internal heat can produce a detectable signal. This is why some rogue planets appear brighter in the infrared than expected. Their heat signatures distinguish them from small, inert objects such as asteroids. The amount of internal heat affects geological activity. A planet with significant residual heat may experience slow tectonic movement or occasional cryovolcanism, where icy materials erupt instead of molten rock. These processes release additional heat and chemicals into subsurface environments. If liquid water exists below the ice, these conditions could create pockets suitable for basic forms of life. The persistence of internal heat depends on the size and composition of the planet. Larger planets cool more slowly because they have more material to store heat. Rocky planets with dense interiors retain heat better than small, porous bodies. Even after billions of years, a planet drifting alone may still hold a warm core. Studying internal heat on rogue planets helps scientists understand the diversity of environments beyond traditional solar systems. It shows that sunlight is not the only driver of planetary conditions. Internal processes, chemical energy, and slow heat release create environments that remain active even in complete darkness. These insights expand the range of possible habitats in the galaxy, highlighting the importance of internal heat in shaping planetary evolution. A rogue planet's surface experiences extreme cold due to the absence of a nearby star, yet its interior can remain surprisingly active. The contrast between a frozen exterior and a potentially warm interior creates a layered structure where different physical processes occur at different depths. The outermost layer, often made of rock or thick ice, cools rapidly by radiating heat into space. Over time, this layer becomes rigid and brittle. Beneath it, however, the trapped internal heat slows the cooling process. The base of the icy shell may sit above a region of partially molten material. If the planet contains large amounts of water, the pressure from the overlying layers can keep the lower ice warm enough to form liquid water. A subsurface ocean forms when internal heat melts ice at depth, even though the surface remains solid. Similar structures exist on moons in our own solar system, demonstrating that sunlight is not required to sustain liquid water. Magnetic fields can arise from the movement of conductive material in the planet's interior. A magnetic field forms when molten metal circulates in a process called a dynamo. Many planets generate magnetic fields through this mechanism. Even without a star, a rogue planet can maintain enough internal heat to keep parts of its core in motion. If conductive layers move at different speeds, they produce electrical currents that generate a magnetic field. A magnetic field affects the behavior of charged particles around the planet. It can trap or repel radiation from interstellar space. Although rogue planets do not face strong stellar winds, they still encounter cosmic rays and charged particles that travel through the galaxy. A magnetic field provides a protective barrier, reducing the amount of radiation that reaches the planet's surface or subsurface environments. To illustrate the thermal structure, consider an insulated blanket paired with a heating pad. The blanket represents the frozen exterior, while the heating pad represents the internal heat source. Even if the room is extremely cold, the combination creates a stable temperature zone between the layers. On a rogue planet, the heat from the interior and the insulating crust form a similar system, allowing liquid layers or geological activity to persist. Geological processes depend heavily on the planet's size and composition. Larger planets cool more slowly and maintain internal heat for longer periods. If the core remains warm enough, convection currents in the mantle may continue for billions of years. These currents can cause slow tectonic shifts or create fractures in the ice above. In icy environments, cryovolcanism may occur, where water, ammonia, or methane erupt from the surface instead of molten rock. The presence of a magnetic field also influences the long-term evolution of the planet. It may help preserve thin atmospheres by reducing atmospheric loss caused by charged particles. Although most rogue planets lose their atmospheres rapidly after ejection, some retain a portion of their gases. A magnetic field can slow the escape of these gases, contributing to a more stable subsurface environment. Understanding how frozen surfaces and molten depths coexist provides insight into the internal dynamics of rogue planets. It shows that even in the coldest and darkest regions of space, geological activity can continue. These environments expand the range of planetary types and highlight the diversity of conditions that exist far from starlight. Rogue planets demonstrate that warmth, structure, and internal motion persist even in isolation, shaping worlds that drift through the galaxy alone. A rogue planet drifting through interstellar space exists in permanent darkness, yet it can still generate and maintain a magnetic field. A magnetic field forms when electrically conductive material inside the planet moves in a coordinated pattern. This movement is part of a process known as the dynamo. On Earth, the dynamo occurs in the liquid outer core, where molten iron circulates due to heat and rotation. The same principle can apply to rogue planets if enough internal heat remains to keep parts of their interior in motion. The internal structure of a rogue planet influences its magnetic behavior. A rocky planet with a metallic core may retain regions of molten metal beneath its surface. Even after billions of years, radioactive decay and residual formation heat can maintain slow convection, the rise and fall of material caused by temperature differences. When the material is conductive, these movements generate electrical currents. The currents, in turn, create magnetic fields that extend outward from the planet. The absence of a star changes the planet's environment, but not the underlying physics of magnetic field generation. While a star provides solar wind that shapes magnetic interactions, a rogue planet is exposed instead to the diffuse environment of the galaxy. Interstellar space contains cosmic rays and charged particles traveling at high speeds. A magnetic field can deflect some of these particles, reducing the amount that reaches the planet's surface. Consider the analogy of a portable battery operating independently of a wall outlet. The battery continues to function as long as it holds internal energy. Similarly, a rogue planet continues to generate a magnetic field as long as its interior retains heat and conductive materials remain in motion. It does not require an external energy source, such as sunlight. The strength of the magnetic field depends on the planet's rotation rate. Faster rotation tends to enhance the dynamo effect by organizing the movement of molten material. Ejected planets may retain much of their original rotation. Over time, their spin slows due to internal friction, but the process is gradual. A planet with a moderate rotation period can sustain a magnetic field long after its surface becomes frozen. The presence of a magnetic field has important consequences for potential subsurface environments. Charged particles can damage molecules that are essential for biological processes. By limiting the influx of high-energy particles, a magnetic field contributes to the stability of chemical systems that might exist deep below the surface. This does not imply that life is present, but it shows that a protective mechanism can exist even without a star. Magnetic fields may also influence the behavior of any remaining atmosphere. Although most rogue planets lose their atmospheres rapidly after ejection, a few may retain thick layers of hydrogen or other gases. A magnetic field can reduce atmospheric loss by guiding charged particles around rather than through the atmosphere. This effect makes the planet's outer layers slightly more stable over long timescales. Studying magnetic fields on rogue planets helps astronomers understand how isolated worlds maintain internal processes. It highlights the role of heat, rotation, and conductive materials in shaping a planet's invisible environment. Even in regions far from starlight, magnetic forces continue to influence the conditions on and beneath the surface, showing that darkness does not eliminate planetary complexity. A rogue planet may carry an atmosphere even after it has been ejected from its original star system, but the behavior of this atmosphere changes dramatically in deep space. Without the heat and light of a nearby star, atmospheric gases begin to cool rapidly. As temperatures fall, heavier molecules condense and freeze, forming layers of ice on the surface. Only the lightest gases, such as hydrogen or helium, remain in a gaseous state under extreme cold. This creates a thin but persistent atmosphere dominated by simple elements. The structure of the atmosphere depends on the planet's mass and composition. A massive planet with strong gravity can retain gases more effectively. Even in the coldest environments, gravity prevents hydrogen from escaping into space. This leads to a dense layer of cold hydrogen hugging the planet's surface. Beneath this layer, the planet may hold a thick ice crust that insulates warmer regions below. Internal heat continues to influence atmospheric behavior. Heat rising from the interior can warm small pockets of gas near the surface. These warmer pockets may circulate slowly, creating minimal weather patterns. The contrast between the frozen surface and the slightly warmer interior produces weak convection currents. On worlds with subsurface oceans, the exchange of heat between the interior and the atmosphere becomes more complex. To illustrate, consider the way air behaves inside a sealed container placed in a freezer. The air cools and contracts, but it does not disappear. The container maintains a small but stable volume of gas. A rogue planet's atmosphere behaves similarly. It becomes compressed and cold, but gravity keeps it in place. Observations reveal that rogue planets with thick atmospheres may emit slightly more infrared radiation than expected. Hydrogen-rich atmospheres can trap heat efficiently. This creates a moderate greenhouse effect, allowing the planet to retain some of its internal warmth. Although the surface remains extremely cold, deeper layers may approach temperatures suitable for maintaining liquid water beneath the ice. The composition of the atmosphere affects its long-term stability. Hydrogen remains gaseous at very low temperatures, but other gases, such as nitrogen or carbon dioxide, freeze out quickly. This selective retention shapes the chemical environment. A simple hydrogen-dominated atmosphere influences surface chemistry and potential reactions that may occur near the boundary between ice and gas. Atmospheric dynamics depend on rotation. A planet with a moderate rotation rate may develop gentle circulation patterns. Slow-moving winds carry heat and trace gases along the surface. In contrast, a planet rotating very slowly may have nearly stagnant atmospheric layers, with minimal movement and very weak mixing. Understanding how atmospheres behave on rogue planets provides insight into the variety of conditions that exist in the galaxy. These worlds show that atmospheres can survive even in extreme cold, shaped by cavity, internal heat, and the physics of gas behavior. Their study expands the range of known planetary environments and highlights the resilience of atmospheric processes, even in complete darkness. A rogue planet carries structural evidence of the forces that shaped its early history. These traces, known as gravitational scars, form when strong interactions disturb the planet's original orbit. During the early stages of planetary formation, large bodies move unpredictably through a young system. Their paths often cross, and gravitational encounters between them transfer momentum and energy. The outcome depends on the masses involved, the distance of the encounter, and the speed at which the bodies pass each other. A close gravitational encounter can stretch a planet's orbit into an elongated path. If the interaction is strong enough, the planet receives a final impulse that sends it out of the system entirely. This escape requires the planet to exceed the system's escape velocity. Escape velocity is the minimum speed an object needs to break free from the gravitational pull of a larger body. Once this threshold is crossed, the planet becomes unbound. The violence of these encounters can leave long-lasting effects on the planet's interior. A large gravitational disturbance can generate intense tidal forces. Tidal forces occur when different parts of a planet feel different gravitational pulls during a close approach. These forces can compress, stretch, or heat the planet. The heating may melt regions of the mantle or create fractures in the crust. Over time, the planet cools, but the structural changes remain. An everyday comparison can be seen in a stress mark on a piece of metal that has been bent. Even after the metal is straightened, the mark shows where the pressure once acted. A rogue planet's gravitational scars serve a similar role. They preserve evidence of the powerful interactions that reshaped it. Computer simulations of early solar system dynamics show that such interactions are common. In crowded protoplanetary environments, planets migrate as they exchange energy with surrounding gas. These migrations create unstable configurations, where planets may occupy overlapping or crossing paths. When two planets approach closely, gravitational forces can act for only a few minutes, yet alter the system permanently. Gravitational scars are not limited to surface features. Deep internal layers may hold compressed regions or irregular patterns in mineral structures. These patterns reveal the strength and direction of past tidal forces. If the planet once hosted a molten core, gravitational heating could have accelerated convection, influencing the development of magnetic fields. In some cases, these events may have stripped away parts of the atmosphere, leaving only thin layers of gas. Observations of exoplanet systems support the idea that gravitational chaos is widespread. Many systems show planets in eccentric or inclined orbits, indicating past gravitational disturbances. Some stars display debris disks made of shattered rock and dust, the remains of collisions or disruptions. These clues suggest that ejection events are part of a broader pattern of instability in young planetary systems. Rogue planets offer a unique record of these early conditions. Their gravitational scars provide tangible evidence of the complex forces that shape them. By studying their internal structure and motion, scientists gain insight into the formation and evolution of planetary systems. These scars reveal that the journey of a planet is rarely smooth, and that violent interactions play a central role in determining a world's ultimate fate. Life typically depends on energy from a nearby star, yet a rogue planet offers a setting where life could exist without sunlight. The possibility arises from the planet's internal heat. Even after being ejected from its original system, a planet retains warmth generated during its formation and through ongoing radioactive decay. This slow but steady energy source can maintain liquid water beneath layers of ice, creating environments similar to subsurface oceans found on Europa or Enceladus. A thick ice shell acts as insulation, trapping heat inside. The pressure from the ice can lower the melting point of water, allowing liquid layers to form while the surface remains completely frozen. The interface between ice and liquid water becomes a zone where chemical reactions occur. If minerals from the rocky mantle mix with liquid water, the environment may support chemistry that resembles hydrothermal systems on Earth. Hydrothermal systems are regions where warm, mineral-rich water flows through cracks in rock. On Earth, such systems support ecosystems that rely on chemical energy rather than sunlight. Microorganisms near hydrothermal vents use chemical reactions to obtain energy, a process known as chemosynthesis. These systems show that life can exist in total darkness, relying entirely on internal planetary processes. A rogue planet with a warm interior could maintain similar hydrothermal vents beneath its ice. The circulation of water through the mantle would supply minerals and heat. Although the overall energy available is far lower than that provided by a star, small pockets of stability could persist for millions or billions of years. These pockets would not require sunlight, only steady chemical gradients and liquid water. An everyday comparison can be made to a well-insulated cooler containing warm water. Even if the surrounding environment is extremely cold, the interior can stay warm for a long time. The heat loss is slow, and the interior remains suitable for processes that depend on moderate temperatures. A rogue planet functions like a large, insulated container where internal conditions differ sharply from the frozen surface. Observational evidence from icy bodies in our solar system supports the idea that subsurface oceans are common. Europa, Enceladus, and Titan all have thick ice shells above liquid layers. Their internal heating comes from tidal forces rather than sunlight, showing that diverse energy sources can create habitable environments. A rogue planet lacks strong tidal forces, but radioactive decay and residual heat can supply enough energy to maintain subsurface water. The chemical composition of a rogue planet influences the potential for life. If the planet contains carbon-based compounds, simple organic molecules may form in the ocean. Interactions between water and rock can produce hydrogen, methane, and other molecules that serve as energy sources for microorganisms. The presence of a magnetic field would reduce radiation exposure, further stabilizing the environment. Studying whether life could survive on rogue planets broadens the definition of habitable worlds. It shows that sunlight is not the only factor that determines where life can develop. Instead, habitability depends on internal heat, chemistry, and the presence of liquid water. Rogue planets illustrate that life may persist in environments once considered too cold and isolated, expanding the range of possible habitats in the galaxy. If Earth were ejected from the solar system and transformed into a rogue planet, the changes would unfold in stages determined by physics, cooling rates, and the behavior of Earth's internal systems. The most immediate change would be the loss of sunlight. Without incoming solar radiation, the planet's surface would begin to cool rapidly. Within weeks, average surface temperatures would fall below freezing. Oceans would start to solidify from the top downward, forming a growing shell of ice across the surface. As months pass, the atmosphere would begin to condense. Water vapor would freeze first, followed by carbon dioxide forming dry ice layers in cold regions. Nitrogen and oxygen would remain gaseous longer because they condense at lower temperatures, but eventually they would freeze out as well. A thin layer of hydrogen, produced slowly by geological processes, might linger, but Earth's atmosphere would collapse into stratified layers of ice. The surface would become silent and still. Although the surface freezes, the interior of Earth remains active. Radioactive decay in the mantle and core would continue to generate heat. This internal heating would slow the cooling process deep underground. Within tens of kilometers beneath the frozen crust, temperatures would remain warm enough to keep rock partially molten. The heat from below would melt pockets of water beneath the ice shell, creating subsurface oceans. These environments would resemble those beneath the ice crusts of Europa or Enceladus, supported entirely by internal energy rather than sunlight. The disappearance of sunlight would end photosynthesis, wiping out surface ecosystems. However, microbial communities that rely on chemical energy, similar to those near Earth's hydrothermal vents, could continue to survive in isolated pockets. These microorganisms depend on chemical reactions involving hydrogen, sulfur, and minerals rather than light. If Earth's ocean floors remained warm, hydrothermal vents could continue to supply energy for life. An everyday comparison can be made to a frozen lake in winter. Even when the surface becomes solid ice, water beneath remains liquid due to heat trapped below. Fish and microorganisms survive in the warmer layers. Earth as a rogue planet would operate on the same principle but at far greater depth and scale. Even after ejection, Earth would maintain its magnetic field for a significant time. The geodynamo in the core driven by convection of molten metal, would continue as long as the core remained hot. This magnetic field would shield subsurface environments from cosmic rays and charged particles drifting through the galaxy. Although surface life would not benefit, deep habitats would remain protected. Geological activity would also continue. Earth's plates would eventually slow as the planet cooled, but thermal gradients in the mantle would drive limited tectonic motion for millions of years. Volcanoes might erupt beneath the ice, creating pockets of heat and chemical nutrients. Cryovolcanic features could form in regions where melted materials push through fractures in the ice shell. Earth's appearance as a rogue planet would be stark. From space, it would look like a dim, frozen sphere with a smooth, reflective surface. The thick ice shell covering the oceans would scatter faint infrared light from internal heat. Occasional cracks could reveal darker layers beneath. No clouds or weather systems would exist, as the atmosphere would largely be locked into ice. Studying what Earth would look like as a rogue planet provides insight into how familiar worlds behave in extreme isolation. It shows that internal heat preserves pockets of habitability even when sunlight disappears. The transformation of Earth into a frozen, drifting world illustrates the resilience of geological and chemical processes and expands the understanding of what planetary environments can look like in deep space. Across many cultures, ancient stories describe wandering worlds, dark omens, or stars that move unpredictably across the night sky. These myths developed long before the concept of rogue planets existed, yet they reflect an intuitive understanding that the heavens can contain objects outside the normal order. Many civilizations viewed wandering lights as symbols of disruption or transformation, associating them with events that broke the stability of everyday life. In early astronomy, the term planet originally referred to any object that wandered across the sky compared to the fixed stars. The visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, were called wanderers because they shifted position over time. These movements inspired stories about deities traveling between realms or celestial beings, influencing human events. Although these planets followed predictable orbits, their unusual behavior created a foundation for imagining worlds that did not follow ordinary rules. Some myths described stars falling from the sky, or worlds being cast out after cosmic conflicts. These stories often portrayed ejection as punishment or consequence. In reality, a planet can be ejected from its system through gravitational interactions, but ancient observers interpreted sudden celestial events, such as comets or meteors, as signs of wandering worlds. These interpretations reflected attempts to explain unpredictable motion using symbolic narratives. An everyday comparison can be seen in the way a person interprets unexplained noises in a dark room. Without clear information, the mind fills in the gaps using familiar patterns or cultural stories. Ancient people approached the sky in a similar way. When they saw an object that moved or behaved strangely, they explained it using mythology rather than physics. As astronomy developed, observations became more precise. Telescopes of the 1600 revealed moons, rings, and new planets, expanding the known structure of the solar system. Yet even with improved instruments, the idea of planets drifting through space without a star remained unimaginable. Scientific models portrayed planetary systems as stable and orderly. Objects that did not fit the model were interpreted as anomalies, not as independent worlds. Despite this, the theme of wandering bodies persisted in literature and philosophy. Some early thinkers speculated about dark stars or isolated worlds traveling between constellations. These ideas were not supported by data, but they hinted at the possibility that the universe might contain unseen objects. Only in the late 20th century did infrared astronomy and microlensing provide evidence for true rogue planets. The connection between ancient myths and modern rogue planets highlights how human imagination responds to the unknown. Myths provided frameworks for interpreting unusual observations long before scientific explanations were available. Although the stories were symbolic, they captured a sense of cosmic movement and instability that aligns loosely with the physics of planetary ejection. Studying these myths helps illustrate how concepts of order and disorder in the sky shaped early worldviews. It shows that the idea of wandering worlds has deep cultural roots, even if the scientific understanding developed much later. Rogue planets turn the symbolic wanderer into a real object, an isolated world traveling through the galaxy, shaped not by legend, but by gravitational dynamics. A rogue planet passing near Earth would create effects determined by its mass, distance, and relative speed. Most rogue planets drift through the galaxy without approaching any particular star system closely. But a near encounter remains a theoretical possibility. Such an event does not require a collision to influence Earth. Gravity alone can alter orbits, redistribute energy, and reshape long-term stability within a planetary system. The most immediate factor is gravitational interaction. A massive rogue planet passing within a few astronomical units of Earth could perturb the orbits of the planets in the solar system. An astronomical unit is the average distance between Earth and the Sunday. If the rogue planet approached this scale, it could shift Earth's orbital path slightly. Even small changes in Earth's orbit could alter climate patterns by changing the amount of solar energy the planet receives. A closer encounter would produce stronger tidal forces. Tidal forces occur when gravity pulls unevenly on different parts of a planet. If a rogue planet passed near Earth, tidal forces could influence ocean levels, crustal stress, and tectonic activity. The effect would depend on mass and distance. A large planet passing close enough could increase seismic activity by redistributing pressure within Earth's crust. An everyday comparison can be seen when a heavy truck passes a parked car. Even without touching the car, the truck creates vibrations and pressure changes in the air. The parked car may shake slightly. A rogue planet acts similarly, but on a gravitational level. Its presence alone influences nearby objects. A very close pass within a fraction of an astronomical unit could destabilize the orbits of moons and smaller bodies. Earth's moon could experience orbital shifts, altering tides and rotation. Asteroids in the inner solar system could be nudged into new paths, potentially increasing impact risks in the distant future. These effects would unfold gradually, shaped by long-term gravitational interactions. However, most rogue planets travel at high speeds relative to star systems. Their fast movement reduces the amount of time spent near any given planet. A brief encounter limits the potential for severe disruption. The gravitational influence would still exist, but it would be short-lived. Only encounters at slow speeds or extremely close distances would produce significant, lasting effects. Observations of exoplanet systems show that gravitational encounters can dramatically reshape planetary architecture. Some systems display highly eccentric orbits, misaligned planets, or debris belts that hint at past disturbances. These findings illustrate that close passes by massive bodies are part of the natural evolution of planetary systems. The likelihood of a rogue planet passing close enough to Earth to cause major disruption is extremely low. The solar system occupies a vast region of space, and planets are tiny compared to the distances between stars. Statistical models indicate that close encounters occur on timescales far longer than the age of human civilization. Studying the potential influence of a rogue planet near Earth helps clarify how gravity shapes the architecture of planetary systems. It reveals the range of possible outcomes, from mild orbital adjustments to large-scale disruptions. Even if such encounters are rare, understanding them provides insight into the dynamic nature of planetary environments and the long-term stability of Earth's orbit. A rogue planet challenges familiar ideas about what it means for a world to have a home. On Earth, the concept of home is tied to stable cycles, day and night, seasonal changes, and a dependable source of light and warmth from the sunday. These regular patterns shape climate, biology, and human culture. A planet bound to a star follows a predictable orbit, and this stability forms the foundation for long-term environmental development. A rogue planet exists outside this structure. Once ejected from its original system, it loses all connection to the cycles and energy sources that previously defined its environment. It travels through the galaxy without a stable orbit, experiencing only the faint glow of distant starlight. The idea of home becomes less connected to a specific place and more connected to internal processes that persist despite external emptiness. The absence of a star means that a rogue planet relies entirely on its own heat. Internal warmth from radioactive decay and residual formation energy becomes the primary driver of geological and chemical activity. This inward-focused energy system contrasts with Earth's outward-driven environment, where sunlight shapes most surface conditions. For a rogue planet, home is defined not by external stability, but by internal endurance. An everyday comparison can be made to a person navigating life after leaving a familiar environment. Without the predictable structure of routine, the person must depend more on internal resources, habits, and resilience. A rogue planet mirrors this situation. Its identity as a world is maintained not through external support, but through the persistence of internal heat, structure, and motion. A drifting world also raises questions about how planetary environments adapt to extreme conditions. Without sunlight, surface ecosystems vanish, and the environment becomes dominated by ice, darkness, and low temperatures. Yet stability persists below the surface. Thick ice layers act as insulation, creating a boundary between the frozen exterior and the warmer interior. Subsurface oceans may remain liquid for billions of years, forming isolated habitats that function independently of any star. The concept of home becomes even more complex when considering potential life. Organisms that evolve on such a world would rely solely on chemical energy. Their survival would depend on reactions involving minerals, water, and heat, rather than on photosynthesis. These ecosystems would exist without any connection to starlight, forming an entirely self-contained biosphere. In this context, home becomes defined by endurance, not by location. Rogue planets also reshape human perspectives about belonging in the universe. Many scientific models portray solar systems as complete, ordered families of planets orbiting a parent star. A rogue planet represents a break from that order. Its existence shows that planetary systems are dynamic and that order can be disrupted. Worlds do not need to remain in the environment where they formed. They can be displaced, reshaped, and sent on new trajectories. Studying rogue planets highlights the flexibility of planetary evolution. It reveals that a world can continue to function even after losing its primary energy source. Geological activity, magnetic fields, and subsurface chemistry do not vanish immediately. Instead, a planet adapts, maintaining internal processes that define its new state. This endurance expands the definition of what a planetary home can be. It suggests that stability can emerge even in isolation, shaped by internal forces rather than by the presence of a parent star. A rogue planet could, in theory, serve as a future refuge for advanced civilizations, though its environment differs sharply from that of a typical habitable world. Its isolation from starlight means it receives no solar energy, creating a surface that is extremely cold and silent. However, this same isolation offers advantages. A rogue planet, traveling far from any star, is shielded from intense radiation, solar storms, and catastrophic stellar events. Its environment remains relatively constant over long periods, governed mostly by internal heat and the slow drift through interstellar space. The interior of a rogue planet provides the most promising potential for habitability. Even in deep space, internal heat from radioactive decay and residual formation energy can maintain subsurface oceans beneath thick layers of ice. These oceans remain insulated from the harsh exterior, forming stable environments with liquid water and motor temperatures. A civilization capable of harnessing geothermal energy could inhabit these deep regions without reliance on sunlight. A practical comparison can be found in underground research facilities on Earth. These structures remain thermally stable and shielded from surface conditions. A similar approach could work on a rogue planet. By constructing habitats within the crust or near heat-producing geological zones, a civilization that access steady energy sources and maintain controlled environments. The thick ice shell covering the surface acts as protective shielding. It blocks cosmic rays, meteor impacts, and other hazards common in interstellar space. This natural barrier reduces the need for additional protective structures. Light sources would need to be artificial, powered by geothermal or nuclear systems. Agriculture could rely on hydroponics or chemical energy pathways rather than sunlight. The greatest challenge lies in mobility. A rogue planet drifts along an unpredictable trajectory, shaped by the gravitational currents of the galaxy. A settlement on such a world would move with it, carried across vast distances over millions of years. While the pace of travel is slow, the perpetual motion could help a civilization avoid large-scale cosmic events, such as supernova explosions or gamma-ray bursts, by reducing exposure to dense stellar regions. A rogue planet also offers strategic advantages. Its low detectability makes it less vulnerable to external threats. Without reflected sunlight or heat signatures comparable to stars, it remains nearly invisible to distant observers. A civilization seeking long-term isolation or protection from interstellar hazards might consider such a world ideal. The potential for using rogue planets as future shelters depends heavily on the technological capabilities of the inhabitants. Advanced systems for excavation, geothermal power generation, atmospheric control, and artificial lighting would be essential. However, these technologies are theoretically achievable, and examples on Earth, such as deep mines or geothermal facilities, demonstrate that humans can already sustain activity in environments completely isolated from sunlight. Studying the possibility of rogue planets as cosmic shelters highlights the adaptability of life and technology. It shows that habitability is not limited to worlds near stars. Instead, stability can come from internal energy sources, protective geological structures, and long-term isolation. Rogue planets present an extreme but viable example of how future civilizations might survive in regions far beyond the reach of starlight. The Milky Way contains an enormous number of worlds that drift in isolation, unbound to any star. These objects, known as rogue planets, may outnumber the planets that orbit stars. Estimates based on gravitational microlensing surveys suggest that billions of planetary mass bodies move silently through the galaxy. Their faintness makes them nearly invisible to traditional telescopes, yet their presence becomes clear when they briefly magnify the light of distant stars. Microlensing offers a unique window into this hidden population. When a rogue planet passes between Earth and a distant star, its gravity bends the starlight and creates a temporary brightening. These events are rare and unpredictable, but large-scale surveys have recorded enough of them to infer the existence of a vast population of free-floating planets. These findings challenge older assumptions about how many planets exist and how planetary systems evolve. Most rogue planets likely originate from unstable early systems. During the formation of a planetary system, gravitational interactions between growing planets can eject smaller or less stable bodies. Over millions of years, these ejected planets disperse throughout the galaxy, following paths set by the Milky Way's gravitational structure. Some are small, comparable to Mars or Earth, while others may be gas giants similar to Jupiter. An everyday analogy can be found in loose leaves carried by shifting winds. Leaves that fall from a tree eventually scatter across wide areas, each following its own path depending on local air currents. Rogue planets behave similarly as they drift along gravitational currents. They do not return to their original systems, but continue traveling across the galaxy's vast structure. The distribution of rogue planets is not uniform. Regions with dense star formation produce more planets, and, as a result, more potential ejections. Young clusters, where stars form in close proximity, create environments where gravitational encounters are common. These interactions increase the chances that planets will be thrown out. Over time, the cluster dissolves, and the ejected planets spread into the larger galactic disk. The isolation of rogue planets makes them difficult to classify. Without a star, they lack visible or infrared signatures associated with reflected sunlight. Their thermal emissions are extremely faint, and only the youngest or most massive rogue planets remain warm enough to detect through infrared surveys. Older, colder planets blend almost completely into the darkness. Despite their invisibility, rogue planets may influence the galaxy in subtle ways. Their combined mass contributes to the overall gravitational environment. In rare cases, a rogue planet may pass through a star-forming region and interact with a young disk, altering the orbits of forming bodies. Larger rogue planets could even capture small moons or debris as they travel. The existence of billions of silent worlds expands the scale of planetary diversity. It shows that planetary formation includes outcomes far beyond stable orbits around stars. Rogue planets occupy the spaces between systems, filling the galaxy with hidden structure. Studying them reveals that the Milky Way is not just a collection of stars, but also a vast landscape of dark, isolated worlds moving independently through interstellar space. Rogue planets and brown dwarfs occupy the lower end of the mass spectrum between planets and stars. Yet their structures and origins differ in important ways. A brown dwarf forms when a collapsing cloud of gas becomes dense enough to heat its interior, but not enough to sustain hydrogen fusion, the process that powers stars. This gives a brown dwarf characteristics that lie between those of a giant planet and a small star. It emits faint infrared light due to residual heat from contraction, gradually cooling over billions of years. A rogue planet, in contrast, does not form through cloud collapse. Most begin inside a planetary system, developing within a protoplanetary disk surrounding a young star. Collisions, migrations, or gravitational disturbances from larger planets can eject them into interstellar space. Their internal heat comes primarily from formation energy and radioactive decay rather than ongoing contraction. As a result, they are cooler and fainter at the same age compared to brown dwarfs. Mass represents one of the clearest distinctions. Brown dwarfs range from roughly 13 to 80 times the mass of Jupiter. Objects above the 13 Jupiter threshold confuse deuterium, a heavier isotope of hydrogen, for a brief period. This fusion is limited and does not produce sustained energy, but it marks a defining physical boundary. Rogue planets typically fall below this mass limit, lacking the conditions required for any fusion. An everyday comparison would be the difference between a weakly glowing coal and a stone warmed by the sunday. The coal produces its own heat for a while due to chemical reactions, similar to how a brown dwarf briefly sustains deuterium fusion. The stone, like a rogue planet, only holds heat it previously absorbed and gradually cools without any internal energy production. The internal structure of a brown dwarf includes layers of dense gas and, in some cases, metallic hydrogen formed under extreme pressure. These conditions resemble the interiors of gas giants, but extend deeper and reach higher temperatures. Rogue planets also contain layered structures, rocky cores, icy shells, or gas envelopes, but they never reach the internal temperatures necessary to form the more extreme phases of matter found in brown dwarfs. Observations highlight additional differences. Brown dwarfs emit detectable infrared radiation throughout much of their lifetimes, making them easier to identify in surveys. Their brightness decreases slowly, following predictable cooling curves. Rogue planets, by contrast, become difficult to detect soon after ejection because their heat escapes quickly. Only the youngest or most massive rogue planets emit enough infrared light to stand out against the cold background of space. Microlensing reveals both types of objects, but it does so without distinguishing between them. The mass of the lensing object determines its classification. Events attributed to brown dwarfs show masses consistent with low-mass stellar remnants. Rogue planet microlensing events cluster at smaller masses, often comparable to Earth, Neptune, or Jupiter. The distinction between the two categories helps clarify how diverse the galaxy's population of dark objects is. Brown dwarfs form as failed stars, shaped by processes comparable to stellar birth. Rogue planets form as displaced components of planetary systems, shaped by orbital dynamics and gravitational interactions. Understanding the differences between them provides insight into both star formation and planetary evolution. Together, these objects illustrate the continuum of masses and structures that exist between planets and stars. Their study expands the picture of how matter organizes itself across the galaxy, showing that not all worlds or star-like bodies fit neatly into traditional categories. A rogue planet moves through the galaxy along a path shaped by large-scale gravitational structures rather than by the pull of a single star. The Milky Way contains spiral arms, dense star clusters, gas clouds, and regions dominated by dark matter. Each of these components contributes to the overall gravitational field. As a rogue planet drifts through space, it responds to these forces gradually, following a slow and continuous trajectory known as a galactic orbit. Unlike planets bound to a star, which follow predictable elliptical paths, rogue planets experience a more fluid form of motion. Their orbits are not closed loops, but long, wandering curves shaped by the mass distribution of the galaxy. Over millions of years, a rogue planet may pass through different regions of the galactic disk, influenced by nearby stars or molecular clouds. These influences act like gentle nudges rather than sudden shifts. The concept of galactic currents provides a helpful analogy. Just as ocean currents guide drifting objects across Earth's seas, gravitational currents guide rogue planets across the galaxy. These currents form from the collective mass of stars, gas, and dark matter. They create slow-moving streams that extend across hundreds or thousands of light years. A rogue planet entering one of these streams continues along it for long periods. Interactions with passing stars can alter the planet's path. A star that comes within a few light years can apply enough gravitational force to slightly change the direction or speed of the rogue planet. These interactions accumulate over time, gradually reshaping its trajectory. The effect is subtle but persistent, similar to how wind patterns slowly adjust the path of a drifting balloon. Occasional encounters with dense regions, such as spiral arms, create more noticeable effects. Spiral arms are areas of higher star density and increased gravitational pull. A rogue planet entering such a region may experience stronger perturbations, altering both its speed and direction. Gas clouds within the arms can also influence the motion, adding small gravitational contributions that accumulate across long distances. Dark matter plays a significant role as well. Although invisible, dark matter contributes most of the galaxy's mass. Its distribution forms a halo around the Milky Way, shaping the gravitational framework in which all objects move. Rogue planets follow paths determined in part by this dark matter halo. Their motion reveals how dark matter influences the dynamics of isolated bodies. An everyday comparison can be found in the way a leaf drifts along a slow river. The leaf responds to currents, eddies, and changes in water depth. It may approach rocks or the shoreline, altering its path slightly, but it continues moving forward, carried by the river's overall flow. A rogue planet follows a similar pattern, guided by the galaxy's underlying structure. Over billions of years, a rogue planet may complete only a few full orbits around the galactic center. The timescale for such an orbit is measured in hundreds of millions of years. During this time, its environment changes gradually. It travels through regions with different star densities, radiation levels, and gas concentrations. These slow transitions shape the long-term conditions on the planet's surface and interior. Studying the drift of rogue planets through galactic currents helps astronomers understand the behavior of isolated bodies in a complex gravitational environment. It shows that even in the vast emptiness between stars, motion is guided by structure. Rogue planets are not aimless objects, but components of a larger pattern shaped by the collective mass of the galaxy. A sunless world reveals aspects of the universe that remain hidden in systems illuminated by stars. Without a central source of light and heat, the structure and behavior of a rogue planet depend entirely on internal processes and on the large-scale gravitational environment of the galaxy. This isolation highlights the role of intrinsic planetary properties and shows how worlds function when external influences are minimal. The absence of sunlight eliminates surface-driven climate systems. No winds form from temperature differences created by day and night cycles. No photosynthesis shapes atmospheric composition. Instead, the planet's conditions evolve from internal heat produced by radioactive decay and residual energy retained from formation. These slow, steady processes create an environment with minimal variation. The stability of this internal energy source demonstrates that planetary activity does not require a star. Subsurface oceans may persist beneath layers of ice. The thickness of the ice insulates the liquid water below, creating a long-lasting thermal environment. This system resembles certain icy moons in the solar system, which maintain internal oceans despite their distance from the sunday. These analogs show that habitable conditions can arise in locations that receive virtually no external energy. The chemical processes within a rogue planet's interior differ from those on illuminated planets. Without sunlight, surface chemistry slows, but reactions within the mantle and subsurface ocean continue at a steady pace. Minerals interact with water, producing gases such as hydrogen and methane. These reactions supply energy sources that could sustain chemical cycles over long periods. The existence of such cycles in darkness expands the framework for understanding where complex chemistry may occur. An everyday comparison can be found in a machine operating in a sealed room. Even without outside input, the internal components continue to function as long as energy remains within the system. A rogue planet functions in a similar way. Its internal machinery, geology, chemistry, and heat flow operates independently of outside light. The physical motion of a rogue planet through the galaxy also reveals information about the larger structure of the Milky Way. Its trajectory follows the gravitational distribution of stars, gas, and dark matter. By studying how isolated planets move, astronomers gain insight into the unseen mass of the galaxy. Rogue planets effectively act as small test particles that map the gravitational field. Their existence challenges traditional definitions of planetary environments. A planet does not need a star to exist, maintain heat, or develop complex internal systems. This shifts the focus from star-dependent habitability to a broader understanding of planetary potential. It emphasizes that the universe contains a wide range of environments, many of which operate under conditions far removed from those around the Sunday. Rogue planets also contribute to understanding how common planetary ejection is in young systems. Their distribution suggests that early solar systems undergo periods of instability, where gravitational interactions scatter planets into interstellar space. This dynamic view of planetary formation contrasts with earlier models that emphasized stability and slow evolution. A Thunless World shows that planetary diversity extends beyond illuminated surfaces and warm atmospheres. It reveals that internal heat, chemistry, and structural processes can sustain long-term activity in conditions that appear inhospitable. By studying these isolated worlds, astronomers gain a deeper understanding of how planets function in the absence of starlight, expanding the range of environments considered possible within the universe.